Welcome back. So still in chapter 3 of Kuchemann, and I wanted to show two more cycles. We were looking at constant pressure heat addition, that's deflagration. And that's certainly true within the ramjet itself. And I wanted to take a look at the case of one, detonation, and then the second one, which Kuchemann does have in the book, which is Carnot. And so the first one, let's do detonation. And now, in the context of when we're talking about this air-breathing propulsion point of view, detonation would actually be a oblique detonation. So here at Venus, we're using a rotating detonation with a rocket engine. So different physics here. But if you had a system and it's being compressed to 1, and then, this is the line of constant pressure, right? Constant pressure. If you did, this is a temperature and entropy. So if you did detonation, which is constant volume heat addition, then you would actually climb to a higher pressure. So this would be state 2, and then your jet is then still at the exhaust pressure. And it's in a different color, showing you what would happen, for the same, let's say you had the same temperature limit. So I'm going to show here for the same limit, then this would have been our old 2, and this would have been our old jet. And so if you can just tell, even by the sort of the height of the lines, you're getting more expansion by doing that constant volume combustion, because you're getting to higher pressure. And so from higher pressure, you have both lower exhaust temperatures. That jet is at a lower exhaust temperature. So you already have an idea that you're using better at getting thermal performance just from that point of view. Okay? But because this is constant volume, we can actually just use our ideal gas law of P is equal to rho RT, and then density is not changing, constant volume, and so we end up having just that P2 over P1 is equal to T2 over T1. So that's pretty easy and helpful. Okay? And so then when we come back to the thermal efficiency, then now it's still going to be the same thing. This is still a system that's flowing. And so it's still appropriate for us to use enthalpies on both situations. Right? So this is the CP up top. You'd have the compression portion. So, what the exhaust portion, T2 minus Tjet, minus T1 minus T0. So just like last time. And then same sort of thing again on the bottom, CP. And this is the heat addition, so T2 minus T1. That's still appropriate. Okay, it's still appropriate. But what we're going to see here is that T2 is far greater than the old, basically the old T1. If we still have our limit, it's the same, but the expansion we're going to get is far different. All right, so from this point of view, that the trick that we did before, we're canceling out the CPs, where this is then 1 minus, and you have a T jet minus T0 over T2 minus T1. That's still the first step in doing that math. Okay, but now we want to take a look at what is T2 to T jet. And this is still isentropic, and so we're going to use those isentropic relations. So I'm going to leave room here to finish and come back, I'll write it over here so it's not directly in front of me. And so, T2 to T jet, using our isentropic relations, is going to be, P2 over P jet, and it's the, okay, should I get that right? Gamma minus 1 over gamma. Okay, well, we know, I'm going to split this up into two different parts. So P2 over P1 and P1 over P0. Because remember that P jet is actually, P jet is the same as P0. It's the atmosphere. And so I'm going to split it like that, say gamma minus 1 over gamma, because P1 over P0 raised to the gamma minus 1 over gamma is simply the relation of T1 to T0. So that, again, this term becomes, including the exponents, becomes just that. And I'm left with P2 over P1 raised to the gamma minus 1 over gamma. So even if we kind of stayed there last time, when we looked at, hey, what is the ratio between T1 and T2 jet? If it's the red condition, so the deflagration, it's the same as this. So this part would have been effectively 1. Okay? right? If P2 or P1 is 1, then right, you can basically see it collapsing to that. So that's the first form. Right? Now I'm going to expand this one more time, because P2 over P1, see over here is actually T2 over T1. And so T1 over T0 and P2 over P1. So that is just T2 over T1 raised to the gamma minus 1 over gamma. And that's equal to T2 over T jet. Right? And then I'm going to split again kind of one more time. So I still have T1 over T0, and I'm going to say T1, it's T2 over T0, and then T0 over T1, because you know those will cancel out, raised to the gamma minus 1 over gamma. And so I'm doing this because I'll be able to combine it here with this T1 and T0 on that side. And so if you take a look at that, that is just T1 over T0. And then, you know, I have a factor of 1 here. If I flip this, I have a minus 1 and a 1 over gamma. So all that's left is actually 1 over gamma of the T1 to T0. And then I still have sort of the T2 to T0 gamma minus 1 over gamma. And that's equal to T2 over T jet. All right, so I can now come back to this equation, and I can substitute T jet in there. And so I'll try to write this not horribly messy. And so that's T2, and then I'm just going to use T1 over T0. I'll go ahead and just put a negative exponent there. 1 over gamma, T2 to T0, gamma minus 1 over gamma, and then minus T0, and then T2 minus T1. All right, so I'm going to pull T0s off of the top and bottom, such that we have 1 minus, and then you see I have a T2 over T1. Sorry, that's not gamma minus 1. This is 1 minus gamma, because I had flipped the negative sign here. And so you can see that that also just gives a negative 1 over gamma on the T2, T1. So, right, in the end, you have, and then if I let's say 1 minus T2 over T0, because I'm left with the 1 over gamma over T1 over T0. And so that is raised to 1 over gamma minus 1. And then I have T2 over T0 minus T1 over T0. Okay, so we're done. Oh shit, I had plots. I needed to put them here. So I'll erase that here in a second and show you some plots. But the key part here is that, again, T1 over T0 is set by our Mach compression, and then our T2 over T0 is set by our temperature limits. And so we can take a look at what that does for our temperature limits. So I'm going to end this, and I'll drop another one, and then we'll show videos, and I'll rewrite some of this here. Okay, see you in a second. Okay, welcome back. So I cleaned off the side of the board so I can show you the graphs. So this is our thermal efficiency. And so the jet efficiency would be unchanged. You would still solve that the same way as before. You have to pay attention. There's a slightly different form for the heat you're allowed to put in, but otherwise it's the same. And so when you come back and do that, what I show here is your oblique detonation, right? So if you can do this, it is going to raise that thermal efficiency up for almost all speeds. In fact, you see quite a drastic jump here if you're able to do oblique detonation at kind of the earlier speeds. And then the top line here is that is in the overall propulsive efficiency. So certainly it goes up, right? This is shifting the whole thing up. Absolutely. And then I'm going to show you what happens on the range side of things. Well, really, you get a big jump here again in kind of the lower speeds, going back to the. It's because you have a fairly big jump there. And so in the end, it does do a little bit better, but certainly what I would say is, from an oblique detonation point of view, this kind of combustion around Mach 3, Mach Mach 2 and Mach 3 might really be the killer. Certainly, if you're trying to do scramjet, oblique detonation, it could be done at supersonic conditions. So this is still showing the whole slowing it down to ramjet. I've not shown this for supersonic combustion. Okay. All right, and then the last thing I wanted to walk through that is also in Kuchemann's book is he did talk about hey, could you do something that's Carnot? And so the Carnot cycle, so TS, is actually where it's constant temperature heat addition. And this would represent, usually represents the most thermally efficient system. And because we're still expanding to constant pressure, you don't get to fully square off the bottom portion here. This would still be your jet exhaust. And so how would you actually go about doing this? Well, the only way to do it would be to have sort of flow over a backward facing step such that you're getting kind of shocks and that you'd have to be supersonic. So Mach would have to be greater than 1. And then you'd have to sort of ignite and heat addition such that as you are going over this, that your pressure is dropping such that, right, if this is, here's P1, right, this is P2, that the pressure is dropping. In fact, you can, if you walk through the relations, because this is constant pressure heat addition, you can actually walk through and show how, P2 is actually P1 E, and then it goes like minus Q over CPT, and then there's a, let's see, a gamma over gamma minus 1. So you can actually walk through and show, hey, what is that pressure decay? Now, I didn't do the final closed form of this, and I didn't show any plots because you have flow over a corner, there is actually pressure changes. You have to account for the fact that V2 is actually greater than V1. So in this condition here, V2 is equal to V1 because of basically because of Bernoulli applies. So it's a little bit more complicated to kind of trace it through in this condition and come up with some plots. So I was going at it for a little while, but decided to stop. But this is sort of an interesting thing that says, hey, you could potentially get really good thermal efficiency if you had a supersonic float and you were able to kind of combust it around the corner. So when we do, we'll mention scramjets and kind of propulsion efficiency at some point in Kuchemann. You'll be able to highlight that, hey, if we might be able to get some portion of this effect where it's kind of burning and combusting as we're expanding the nozzle portion, and that would lead to what it would let you do is that you could have higher compression here because of your material. This is always kind of the topmost material is always your choice. So it would let you take more compression from the air, and then as you're adding heat, it's not it's not sending you through the roof on the temperature. So certainly interesting. Could be some really interesting technology in that path, but more so again highlighting that it's most likely used in a scramjet point of view. All right, we'll see you next time.